Hello everyone, welcome to this problem where we are going to dive into find if array can be sorted. So basically you receive as input an array of integer. You're supposed to find out if the array can be sorted. So basically any array can be sorted for sure. But now in this array we are performing swap only if one condition is respected. That means let's say I receive this element as input. There should be a condition that needs to be respected in order for me to be able to swap those two elements. So if two elements are not actually sorted and they are not respecting the condition that has been stated here, that means those elements cannot be swapped and therefore the array cannot be sorted. So that is the logic. Now what is the condition that needs to be respected? In one operation, you can swap any two adjacent elements if they have the same number of set bits. So let's take this element for instance. So the binary representation of 2 is 1, 0. So we have one set bit, the number of 1. And if actually you find yourself with those two elements with different number of bits, with different number of 1 in the binary representation, not actually sorted, definitely you cannot swap them, so you need to return a false. So for us to solve this, we are going to dive into like the direct implementation of bubble sort, but including that condition. And after that, we are going to discuss another solution which is a little bit more efficient. But since we have like small input, we can see that the length of num is actually small. It will not make a big difference, but it's nice to know the two techniques because it can help you during an interview. Okay, so let's dive into the explanation of the first one. So let's say this is an array. So since this is an array, this is actually, let me take the red one. This is actually the binary representation of 2 is actually 1, 0. The binary representation of 8 is actually 1, 0, 0, 0. And the binary representation of 4 is actually 1, 0, 0. So those three elements are actually having the same number of bit sets. So this is actually kind of separate that element can be swapped into. But this one is actually is 1, 1, 0, 0, 0, I guess. And this one is 1, 1, 0, 0. And this one is actually 1, 1, 0, 0, 0, 0. Okay, this is actually another subset. So basically all the elements in this subset can be swapped. So this one can be swapped and then you end up with 2, 4, 8. And the same inside here, this one can be swapped and then you end up with 12, 24 and 48. And then after performing this, you can see that the overall array has been swapped, is swapped actually. So you can return true. But if you find yourself sorting the one part of the array and sorting the other part of the array, and then you don't have this actually continuity of an array being sorted, there's nothing you can do because those two elements cannot be swapped. Okay, so now for us to solve this, how are we going to approach it? So the first approach is to use a bubble sort with the condition of checking if they have the same bit set. So we're just going to, if you know about bubble sort is this technique where you actually, let me show you this. So this is a simple implementation of bubble sort. So you can see that you have your initial array, it is actually swapping. You have your initial array and then you are checking two consecutive elements. If they are not sorted, you swap them and then you move forward. If they are not sorted, you swap them. After each iteration of the bubble sort algorithm, you are going to sort the last element. Now you take again, you do the same. It's going to sort one element. So if you have this as input, after the first iteration, this one is going to be sorted. Now after the second iteration, this one is going to be sorted until you have all your array being sorted. So you are going to have one loop for n time because you want the n element to be sorted, and then now for each of the iteration you now apply the swap while moving. Okay, so let us implement that. and let us see what they will give. So we are going to have for moving to num.size I++. So this is the number of time I want to perform the swap, and then now okay, this is now the inner loop. And then now before performing the swap, because usually you just need to check in the bubble, so you need to check if nums of g is actually in this case this is actually smaller than nums of g minus 1. Then you perform the swap of nums of g and num of g minus 1. So this is the basic implementation of the bubble sort. But now not all the time we are going to do this. The first thing we need to check is that if they are actually small, if there is a need of swapping, we need to check another thing. So we need to make sure that let's say we need to make sure that if the bit set of 9, why 9? Because the maximum value is 2 power of 8, and to encode 2 power of 8 we need 9 bits, so 9 is actually okay. So bit set of 9 of nums of g dot size now dot count, if they are actually equal, then we can perform a swap. It's easy to get something wrong here. Okay, so we need to check again if they are actually different. That means if they are actually different, what does that mean? That means you are in a situation where you need to perform a swap, but you cannot perform the swap because the number of bits is actually different, so you return false. If you find yourself with a situation where you need to perform a swap but you cannot swap, that means the array will not be sorted at the end, so you return false, right? And otherwise you swap, and then at the end here you can return true. That means if you find yourself here, you can return true. Let us run and see. So we are missing one thing. What am I missing? Let me see. We are comparing g to g minus 1. Okay. Oh, yi is g minus 1. Perfect. Let us submit. Working pretty fine. So this is the first approach of solving this, and it's actually pretty straightforward. You apply the bubble sort with one condition, which is actually comparing the number of bits. We share the logic of this. So now another way to solve this is to transform this array into another array and just check if the result is sort. What does that mean? That means, let's say I receive this as input. Basically, since those elements are actually, if you have a group of elements sharing the same bit, at the end what we need to have, in fact what is important for us, is to have the maximum, which is the minimum, which is 2, and the maximum, which is actually in this case 8. The same for this one. What we need to have is the minimum, which is 12, and the maximum, which is 48. And then why continue, we can just keep the minimum and the maximum of each of the subset, and after that we just need to check if the result array is actually solved. This can be done in big of n. You don't need to have a double for loop. So the idea will be, okay, initially you can have 2 elements of your array with the first, like you can have something like 2 2. Now for each of the element, the first bit, the first pair of the element is going to take the minimum of the value that was there and the incoming value, and the biggest one is going to take the maximum. So by doing so, you are going to transform each of the sub element into an array where we are going to make abstraction of the middle element, and at the end, if this one is solved, then it's perfect. it is possible, otherwise it's not possible. So try to implement that. Here's my own implementation of that. So for me to implement that, I will need to have my vector here of int. I will call it element, and then now what I will do here, I will initialize the element of my array with the first. So I'll say element dot size, element dot pushback, sorry, of names dot 0. So I need, each set of bit is going to have a minimum and a maximum, so I need to have 2. So I just put it 2 times. Why? So I'm going to have 2 at the beginning. This one is going to make me have 2 8. This one will come, I will say have 2 8 because you will not update anything, and so on. So what am I doing? I'm starting at 1 because I've already added the first element. I don't need this inner loop. And now for each of the element, I just need to check. I just need to I need to check if actually the bit set of 9 of names of I is actually equal to the bit set of 9 of names dot I minus 1 dot count. I need to have the dot count here and a sim here. So what is actually this indicating to me? This is indicating that the new element that is coming is having the same bit set with the previous one, so they are actually sharing the same subarray. If they are sharing the same subarray, I just need to make update. The update is actually saying element dot size minus 1 is actually equal to the maximum of element dot size minus 1 and what, and num of I. And for the element minus 2, which is so element minus 1 will always be this one, and element minus 2 will always be this one, and we agree that the first one is the minimum and the second one is the maximum. This was the second one, and this is actually the minimum, and it should be minus 2 here. And otherwise, if they are not actually sharing, if they don't have the same number of bit count, that means it's actually a new subarray. A new subarray will actually introduce 2 new elements that are going to be used to compute the minimum and the maximum. How do we do that? So we just need to do the element dot pushback with num of I, and we do this. We do this 2 times. 2 times, one for the minimum and one for the maximum. And at the end, we just need to return is sorted of element dot begin and element dot end. Let us run and see. Oh, working, you see. So this is actually a different logic with just one loop, and this is definitely more efficient than the previous one, even though in this scenario, let me run again, let me submit. You see, the result is way interesting than the previous one. So this is one of my approaches of solving this. I hope you do enjoy it. Feel free to give me any input. I'll be really happy to interact with you regarding this. See you tomorrow for a new video. Take care, keep learning.